In 1901, divers exploring a shipwreck off the coast of Antikythera discovered a heavily encrusted, unnatural rectangular shape buried in the seafloor. They had found a machine capable of predicting celestial events with exact precision, though they didn't know it yet. What was actually recovered from the site looked like little more than calcified lumps of bronze. For decades, these fragments were treated as archaeological debris, corroded, green, and seemingly devoid of any complex function. That perception changed when early X-ray analysis looked beneath the decay. Deep inside the fragments, the imaging revealed a deliberate, interlocking system of hidden gear teeth. The presence of a 2,000-year-old precision analog computer shifts the timeline of ancient technological development by centuries. The internal architecture shows a functional machine designed to map out the positions of the sun and moon with mathematical precision. To achieve this, the builders utilized the Metonic cycle, a 19-year lunar period used by ancient astronomers to synchronize the solar year with the phases of the moon. The engineers physically hard-coded this abstract math into the mechanism. By selecting specific gear ratios, they forced one wheel to rotate exactly 19 times for every single cycle of the larger wheel it drove. Translating these long-term astronomical cycles into a confined physical mechanism indicates that the builders integrated advanced mathematics with mechanical engineering. Tracking the moon is a significant mechanical challenge. Because its orbit is elliptical, it appears to speed up and slow down from our perspective on Earth, making it impossible to track with simple, constant-speed gears. The ancient solution was differential gearing. A pin slides within a slot on an adjacent gear. As the assembly rotates, the changing position creates a variable output speed. This variation simulates the moon's velocity, providing a physical model of its irregular motion through the sky. The principle of differential gearing does not appear in the historical record again for over 1,000 years. This component indicates the mechanism was a predictive computational system, adjusting its output based on real-world astronomical observations. Beyond the theory of its motion, the physical construction of the device introduces a second mystery: how these parts were manufactured without modern machine tools. The gear teeth are cut with a level of uniformity that suggests the use of standardized templates or guiding systems, tools that have since been lost to time. This chart details the celestial events the device was built to track. The exterior featured dials for eclipses, lunar phases, and the changing seasons. These same dials also tracked the 4-year cycles of the Olympic Games. By combining the calendar of the gods with the cycles of the cosmos, the machine demonstrates that ancient Greeks viewed scientific knowledge and societal life as parts of a single, interconnected system. This graph illustrates the history of mechanical complexity. The Antikythera mechanism creates a sharp peak in ancient Greece, followed by a sudden drop and a 1,000-year flatline before complex gear systems appear again during the Renaissance. It suggests that advanced technological understanding is not always cumulative. It can be entirely lost and take millennia to reemerge. No other devices, blueprints, or descriptions of this complexity have survived from this era. We are inferring an entire lost tradition of engineering from a single damaged artifact. Despite over a century of study, we have recovered only about 1/3 of the original mechanism. Most of the internal architecture remains a void. Because the internal system is incomplete, we cannot confirm its primary role, whether it was an educational tool, a display of intellectual prestige, or something else entirely. If a machine this advanced could be forgotten, it raises the question of what other ancient capabilities have been erased by time.